Thanks for the kind introduction, and I'm very excited to be here today. So today I'm going to be talking about the future with affordable self-driving cars, and I want to talk I'm not going to go into a lot of details. Instead, I'm going to tell you a little bit of the different things that we have done over the past 2 years to build, the different autonomous systems that we have as of today. So without further ado, let me tell you into what you need in order to make affordable self-driving cars. So there is basically like 4 different aspects that you need to care about if you want to build self-driving cars at a scale. The first thing is obviously you need the hardware, right? You need the vehicle platform. And these vehicles are different than regular vehicles in the sense that they need to have things such as redundant compute, for example, such that if one of the computes fails, right, you have a way to drive safely. You also need the self-driving system, which is basically the brain of the car, which is what I'm going to be talking today. But at the same time, you need a way to operate the large fleet of vehicles that potentially you might have, as well as a network in order to guide where these vehicles should go from point A to point B. Now, at Uber, we know how to build networks, right? This is what we do for a living. And we build the brain of the self-driving car, as well as some of the sensors and hardware components. But we don't build vehicles. Instead, we partner with OEMs such as Toyota, for example, or Volvo, in order to come up with what those vehicles should look like. Now, in today's presentation, I'm going to be focusing on 2 aspects. First, I'm going to talk about sort of a history of the different autonomy systems to show you into where we are today. And then I'm going to be talking about also simulation in order to be able to test self-driving systems and at the same time potentially also create new training data for building better autonomy systems. And most of the talk I will spend in terms of autonomy. Now, if we look at modern self-driving systems, right, the question is, well, how can we use AI in order to improve the robustness and the accuracy, say, of autonomous systems? So there is typically like 2 main, very different paradigms to do so. A very popular approach, which is typically done in academia, is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements. For example, the LiDAR, images, radar, and the output is the information necessary for the self-driving car to drive. This can be, for example, steering command as well as acceleration. The advantage of such an approach is that it's actually very easy to get a prototype with just a few lines of code with your favorite system, whether it is TensorFlow or PyTorch. Furthermore, the system is trained for the end task, which is the task of driving, since the loss function typically comes at the end of the network. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge, and thus it is difficult to make the system respect the rules of traffic, which is something that we must do by law. It also has no interpretability, which poses a problem for the system's validation and safety. So although you see this a lot in academia, you don't see this paradigm in industry. An alternative is a traditional software stack, which is composed of a set of modules, as you see here in the image. So every fraction of a second, what happens is that you basically the vehicle senses the environment, and this is illustrated here with a bird's eye view of the LiDAR point cloud. Which basically means that you are seeing the scene from the top, right? Where this white stuff here in the image basically represents LiDAR point clouds. The first task that then the vehicle does once it receives the sensor data is to localize where it is in the world with precision of a few centimeters. And this is done not only to route the vehicle from point A to point B, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene. Here I depict vehicles with bounding boxes and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning system ensures that the motion planning system focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. Now, the control system then ensures that the trajectory that we intended to execute, which is the one given by the motion planner, is indeed the one that the vehicle does. And there might be deviations due to things such as friction or the fact that we might not have exactly the vehicle dynamics. This full process is then repeated every fraction of a second, typically 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations, and it is easy to incorporate prior knowledge. These were the things that were actually difficult in the end-to-end approach. However, reaction time is typically large here as computation adds up. Right, you have to sum the computation of every one of these models. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes that somebody else has done. As in industry, typically you have hundreds of people working in autonomy. This is actually a very big deal. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate for better driving. For example, our detection systems might be trained to have very good PR curves, precision recall curves, but that doesn't mean that improving that is going to improve how the whole system drives. Now, the vision of what we have been building at Uber is something different from both of these approaches. And it has advantages of both the end-to-end and traditional engineering approaches, but without inherently their respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly the developer productivity problem I was mentioning. As computation is now shared across modules, the resulting reaction time is much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. So let me show you how what is the work that we did in order to develop algorithms that actually follow this vision. Our first attempt towards this vision focused on developing approaches that can do joint perception and prediction. This is basically 2/3 of the software stack within a single algorithm. Fast and Furious was the first thing that we showcased 2 years ago at CVPR. And the idea is very simple. You can create these bird's-eye view representations by voxelizing the LiDAR. And in this case, we use a set of frames. You can use your favorite neural network architecture to create some LiDAR features that you use to decode in terms of detection scores, as well as regression that basically produces the location of this bounding box in the next few seconds. This technique actually works extremely well. And in this case here, we can do very fast computation, only in 35 milliseconds. You can actually produce the results that I'm showing here in the video. The other thing that this thing can do is also it can generate tracking at the same time. So just for you to interpret the video, what you can see here is we're gonna, in this case, detect vehicles. The vehicles that appear with the same color over time, it means that they are being tracked as the same ID. And these points that emanate from the bounding boxes basically represent what is the location that we predict for that vehicle in the next few seconds. If you see a single point, it means that that vehicle is predicted to be static. If you see that those points are actually separate, very separate, far apart, it means that this vehicle is predicted to have higher velocity. So one of the things that we noticed is that you can do like very accurate prediction by a single system. And this was actually a big breakthrough in how to think about perception and prediction systems for self-driving. Now, this was a fairly simplistic approach, right? We basically have a neural network that was able to exploit LiDAR and produce detections as well as predictions into the future. One of the things that we know is that if you look at vehicles, right, they actually interact with each other. And if you see, for example, two vehicles coming to an intersection, typically you don't expect them to collide. Instead, you expect them to somehow interact with each other, and one of these vehicles is going to pass before the other, and the other one is just going to yield to that vehicle, right? So it's very important that our systems also are able to reason about these interactions. So let me show you how we can actually do this. So you can take something that has a similar sort of beginning of the architecture as before, where we're going to have these voxelized layer representations. The other thing that we're going to add here is a representation of the high definition map, which is shown here in the bottom. And this is important in order to have accurate predictions. Then we're going to compute some feature representations for every voxel in this bird's eye view representation. And we're going to perform detection by basically looking at the activations of where we see things that are actually high likelihood to contain a vehicle. Then we're going to create, by rotated ROI pooling, feature representations for these actors. And we're going to exploit a graph neural network, as you see over here, that is spatially aware in order to reason about the interactions between all these different actors that are in the scene. And the other thing that is important is not only we will take into account the interactions, but we're going to predict a probability distribution over trajectories. And this is important because having a good notion of uncertainty is very important for self-driving, right? For example, knowing that something is you're not very certain about is important because, for example, the motion planner could decide to slow down such that you don't end up with something that is bad. So let me show you how this works with a video. So in this case here, you see the detections as well as the predictions into the future. And in order to make these predictions, we take into account with this, especially our graph neural network, the relationships between all these different actors. And you see that you have these nice compliant behaviors where the predictions don't collide into the future. Now, in this type of model, what we typically model is the marginal distribution, which is the probability across, the probability of the potential trajectories that every vehicle might do. And yes, in order to come up with that marginal distribution, we take into account their interactions, but at the end of the day, we only have access to the marginal distribution. Now, if we sample in order to do planning from that marginal distribution, we can have the following problem. So I'm going to illustrate this with an example where we have two vehicles. One is already driving on the road, and the other one is sort of going to merge into this road. So one possibility, if we sample from this marginal distribution, is that the first car decides to accelerate, right, and go fast, and the second car is actually going to slow down. So this is a scenario that would be great for us to predict. Alternatively, we could predict something different, which is this first car is slower, and then the other car is going to accelerate and can basically incorporate nicely. This is also a nice scenario to predict. We could also predict something where both vehicles slow down, because typically you sample independently from the marginal distribution, and this starts to be not so good. Furthermore, we could actually have even worse even worse samples if basically it turns out that we sample that both vehicles decide to accelerate and basically will end up in a collision. This is not something that we're going to see in practice with very high probability, right? So just sampling the marginals is not a good idea. So instead, what you would like to have is a way to sample distributions across all the actors such that they are socially consistent, right? And in order to do so, yes, we need to take into account the interactions, but the samples have to be such that you sample consistently the full scene instead of sampling from the marginal distribution. So the way that you can do something like this is by incorporating latent variable models. In this case, we call it ILVM, or implicit latent variable model, where the idea is the following. We are still going to have HD maps as well as lidar point clouds in order to estimate some representation for each vehicle. And then once we detect the vehicles, right, we are still going to pool the features. So that's what it represents here. But now what we're going to have is we're going to do some representation for each one of them. And we are going to use a graph neural network in order to basically encode a latent variable model, which is the probability of the latent given the observations. And then, so this is the encoder, and we're going to use as a decoder another graph neural network also that takes into account all the interactions in order to come up with the final trajectories. Now, what is interesting in this model is that it's distributed, but it takes into account distributed, meaning that we have as many latent values as we have number of factors. So it generalizes to an arbitrary number of factors, which is important, right, in self-driving. But at the same time, all the stochasticity comes in this latent variable model, meaning that once you sample from the latent variables, the coding is deterministic. So this allows you to have a representation that takes into account all the interactions between the different actors. And it's very efficient because simply you need to just sample from the latent variable and then just decode. And this sample of the latent variable is just conditioned on the observations. So the other thing that is interesting is that you can train this whole thing end to end. And basically you can have a loss for detection, a loss for reconstruction here, which is prediction. And then this is like, you can think of it as a sophisticated conditional VAE. So you have your standard KL loss between the prior and the encoded. Now, it turns out that this actually works extremely well. And the fact that you have these consistent samples allows you to create, I guess, realizations of what the future might look like, where you almost, you have very low probability of having collisions across actors. And this is very important for the motion planner. At the same time, the standard metrics in terms of how well you predict, this also results in much better predictions than any of the typical approaches that you see here, for example, Waymo's multipath over here. But let me show you this in practice. Okay, so this is sort of the results that you can get. So the input here is raw sensor data and the high definition maps. And what I'm showing you here is samples by drawing, the results by drawing a few samples from this latent distribution and just decoding. So you see that it's multimodal, right? Particularly when you have potential turns, right? You start seeing this multiple modes of the distribution at the same time as there is multimodality across the speed, right? And it's able to very nicely, for all predictions, follow well the maps, which is actually pretty difficult to do with these neural networks. What is more important is that we can then plug this perception and prediction system, ILVM, into motion planning and compare to all the other approaches that exist out there in the literature. And as you see over here, you end up with a planning that is much safer. So end up in open loop, much less collisions. And at the same time, it's more comfortable, meaning that you have to slam on the brake less and you have less jerks, for example, and you have is very similar to what will be human demonstrations while maintaining the progress. So basically, not only you have better prediction metrics, right, but you end up with much better planning metrics as well, which is what matters for self-driving. Now, I talk a little bit about how to build sophisticated joint perception and prediction systems where we went from something that predicted independently every actor to things that can take into account with graph neural networks the interactions to something where we can actually sample the full scene. But there is an inherent difficulty, if you think about it, about the joint perception and prediction problem, or even about the perception problem, which is the following. If you look at your observations, and I'm showing this here with the later here, there is some actors where it's actually really easy to detect and predict. For example, this actor nearby, right, which I'm zooming in, you see that there is a lot of observations, right? So we have a very nice evidence to know where this thing is. For things that are far away, there is not that many observations, right? And it's actually going to be very difficult to say that this is a vehicle and to say, what is the shape of this vehicle in order to place a bounding box. So that problem is much harder. Furthermore, because of occlusions, there is areas where it's going to be very difficult to actually detect and predict what's happening. And in many safety critical situations, predicting things that can come out of occlusions is of extreme importance in order to drive safely. So we look at is there a different way to tackle this problem such that we could see through occlusions and see much better far away? So the idea is very simple, right? That if we were to have a fleet of self-driving cars instead of a single self-driving car, we should be able to transmit information between these vehicles such that we could see farther and we could see through these occlusions. And then suddenly we will have a much better picture of what's happening around us, and we can do both perception and prediction with a much higher degree of fidelity. So I'm showing you here into what will happen in practice. So in the left-hand side, you see a three-dimensional scene, and the self-driving vehicles are in different colors, and regular vehicles are simply these LiDAR point clouds that you see. And on the right-hand side, you see for every one of these vehicles color-coded, what will be the observations that they will be seeing if they were driving around this scene here. Okay, so you see that they are seeing very different things, right? And you should be able to combine this information to see better. So let's see how we can do this. So the first thing to think about is, how can I combine the information between all these different self-driving vehicles such that I can predict better? But I need to be careful, right? Because I need to do so, but also taking into account the fact that I cannot transmit infinite information, right? So is there a way to transmit very little information and at the same time, get the best trade-off of how much I need to send versus how much I can help my perception and prediction system? So there is sort of three different strategies that you can do in order to decide what to transmit. On one side, you can say, well, I'm going to just transmit the raw sensor data, and this way, every vehicle will have all the information that the other vehicles have. Now, the good thing about this is that you actually preserve all the information. You haven't done any approximations, right? So that's great. But you're going to need to send a lot of information, which is going to be difficult if you have a bandwidth constrained system as you typically have in practice. Furthermore, this scales pretty badly in terms of, if I have more sensors, I need to send more information. And what is even worse is the fact that the latency problem is already difficult for a self-driving car to reason in real time with its own sensory data. If now I have many vehicles sending more sensory data, it's going to be extremely overwhelmed, and it's going to be very hard to come up with any output. So that's not going to be a safe system. An alternative is to say, well, maybe what I can do is I can perform perception and prediction for every vehicle independently, and then I can send the information of what they think about the scene to everybody else's in order to refine the predictions, the perception and predictions. Now, the good thing is that this is very compact, so it's very cheap to transmit. So that's great. We can use very simplistic hardware that costs nothing. But it's very limited in terms of you have already reduced all the information that you had into something very tiny, and it's it's going to be hard to decide if the different perception and prediction outputs differ between different vehicles. How do I know who to trust? Right, and even just sending some uncertainty estimates typically is very difficult to have good uncertainty, so that's not going to cut it either. So what we argue is that there is something different that you can do where you end up with the best trade-off between bandwidth transmission as well, required bandwidth transmission, as well as accuracy improvements for perception and prediction. And the idea is to see this system as a distributed compute system, where every vehicle is going to receive its own observations, right, from for example, its LiDAR. It's going to create some intermediate representations. Then we're going to compress those representations, and that's what they're going to send to the medium. Then we're going to gather all the information that is transmitted, and then this transmission will be basically exploited for joint perception and prediction. So let me explain this with an illustration. Right, so this is a representation that is ends up being with the best trade-off. So we have the different SDVs. There is 3 here, and each one receives those observations and computes this intermediate representation. Right, so it's a distributed system. Then we're going to compress this intermediate representation, send the information, and then every vehicle captures all the information from the other vehicles and uses a spatially aware graph neural network in order to use all the information from all the different vehicles to come up with a better representation of what's happening in the scene. Now, once again, this graph neural network is especially aware because these intermediate representations, in our case, are actually spatially aware, meaning that every pixel in this bird's eye view representation represents a particular physical area in the scene. So it turns out that this actually works really well and requires, so in this case, I'm showing in terms of perception with mean AP and prediction with L2 and collision rate. But what is more important is that the influence of how well you do scales almost linearly with the number of vehicles that are in the scene. And this is very good news, right? Because the more information that you have, there is a lot of possible gain if you transmit this information. The particular graph neural network instantiation that we have is actually very robust to things such as imperfect localization of where every vehicle is with respect to each other, which is something that we send as well as information. So that's something that is very important, right? Because you might have localization systems that are not so precise sometimes. Also, it's very robust to basically the delay messages. And this happens because every vehicle captures information in an asynchronous manner, and there is going to be transmission delays that are dependent also of how much information you send. So it's something that you need to be robust. And in this case, by doing this graph neural network and this by passing these intermediate representations, you end up with something very, very robust, as you see here with the V2VNet. Is our approach basically versus if you just fuse the input or if you fuse the output, right? There is big improvements in terms of performance. All right, so I mentioned a lot of things about joint perception and prediction, but my spiel at the beginning was that we want to have a single AI system that is able to do everything. And so far, I have only tell you about how can we do with a single algorithm joint perception and prediction, potentially using information from many vehicles. So let's look at the next section, which is on interpretable neural motion planners. So the idea now is that we're going to push not only to do detection and prediction, but on top of this, we're going to do motion planning as well with the same algorithm. So the first version of an interpretable neural motion planner, we presented this a year ago at CVPR, and the idea is the following. So we're going to treat this as a multitask problem, where basically we have as input the LiDAR point clouds for the past consecutive T-frames. We have our high definition maps. We're going to compute some representations of the scene. And then we're going to perform detection, prediction into the future, as well as we're going to predict a cost volume that we're going to use for planning. And this cost volume, what it represents is basically what will be the cost for the self-driving vehicle to be at every possible location and time within the planning horizon. Okay? So you can think of this as treating this as a structured problem, which is non-parametric, where basically you learn the cost of all the possible locations and times where you could be. And given this feed-forward computation, now the question is, how do I obtain my plan trajectory? So what we do is that we sample a set of physically realizable trajectories. In this case, it's on the thousands of these trajectories. Now, for every one of these trajectories, you can compute its cost by simply indexing this cost volume that you have computed. And then you simply select the trajectory that has the minimum cost. So it's actually a very, very simple planner. The good news is that indexing is very fast on GPUs, right? And computing minimum cost is operations that we are used to do as well within GPUs. So you can do this in a very, very efficient manner. You can also train this end-to-end, right? Where you are going to have a loss for detection and a loss for prediction. And for the planning, it's a little bit more complicated in the sense that we don't know what the cost volume should be. Otherwise, we will have the perfect planner, right? Instead, what we do is we use max margin loss, where we basically say that we prefer trajectories that are close to the human and that they should not violate the rules of traffic and they should not collide. And basically, you can backpropagate through this loss and learn all the network at once. So let me show you what this does with a video. In this case, what we're going to depict is the detections, the predictions into the future. Now we're going to be doing 3 seconds into the horizon. And what I'm showing you here with colors is basically this cost volume, which is 3-dimensional. I'm going to project it to 2 dimensions. And I'm going to use different colors for the different timestamps of the prediction horizon. And I'm only going to show you areas of very low cost, which you are likely to use as the potential trajectories. Okay, so otherwise it will be too overwhelming. But what you can see is that this non-parametric cost function basically can capture multimodality really nicely, understands that it needs to avoid collisions, for example, by changing lanes, right, is able to do very difficult maneuvers like going around vehicles that park or in the middle of the road, etc. And all this is trained with simply a few bounding boxes, as well as just to imitate what the humans do. So this was a great first attempt, and we could do something where we have interpretable representations, and we can do perception, prediction, and motion planning. Now, what's important on this is that not only it's good to to be able to get all the way to motion planner, but what is very, very important is that the perception and prediction system are trained for the end task, so you end up with much better perception and much better prediction. However, there is a few caveats in this approach. The first one is that, well, in this particular case, it was multimodal for the self-driving vehicle in terms of planning, but it was not multimodal in terms of the probability distribution for how every other actor, our understanding of how every other actor will behave into the future, right? So that's a problem. It was deterministic. At the same time, we treat this as a multitask learning problem, which means that condition on the features, the tasks are independent, right? So planning does not explicitly condition on your output of prediction and perception, and that's not great. And although we use information and prior knowledge in the loss function, this is not used by the model, which means that there is some chance that you end up in collisions, or you don't follow traffic rules or dynamical constraints, resulting in plans that are not realistic. So the next version of this that we presented, I guess, a few weeks ago at the CCV is what we call the deep structure self-driving network. It's basically an end-to-end system where instead of treating this as multitask, we're going to do this in a structured way, such that we take into account the fact that these tasks will be consistent. We can use our prior knowledge, and we explicitly condition on the prediction and create this also multimodal social consistent interactions. And so how do we do this? So now, instead of right before we have these independent tasks, now we're going to have something that looks a little bit more like the traditional approach. But what is different is that we are able to reduce the different computations along the way for the different models. So that's important. And also, we're going to be able to train this thing end to end. And the other thing that is important is that this prediction model actually now is going to be much more sophisticated. It's going to be a Markov random field. Where basically we're going to represent, how likely is every trajectory, right? How good it is, as well as we're going to represent the fact that the different actors should not collide. Okay, and so inference in this model is going to be a little bit harder in the sense that it's not just feed forward, right? So we basically do feed forward. We detect, we create our Markov random field. We can perform inference by using bit propagation, which is the same as unrolling. You can unroll it so that it's like you can think of it as a recurrent network, and it basically goes to our planning model here, which is the planning model uses a combination of cost, where some of it is coming out of a purely learned cost, and some of it is safety costs that are actually hand-coded, and that allows you to guarantee that you respect the rules of traffic. So let me show you some qualitative results. So what you see here is that you end up, for every actor, you have these nice predictions, right? When things are static or they are parked, you have this very nice, all the probability distribution concentrated. And as you go, for things that are moving, as you go farther in time, you see that the probability fans out. So your uncertainty increases. And you have this inherent multimodality, right? For some of the, in the case that you could actually do many things like turning left, turning right, as well as continue straight. And this is another example where you see if you continue straight, there is little uncertainty in terms of especially where you're going, but it's temporal, right? And if you're turning, there is many things that you can start to do. So this is just showing with a video, and the plan is shown here in red. So this method results in much better prediction metrics, and particularly these predictions are now socially compliant. And in terms of the motion planning, is also much better, particularly in terms of safety, that the first iteration that we did before. Now, this type of planner still has one difficulty or one problem, which is the following, is that for anything that is based on detection, right? It's the same for the traditional software stack. What happens is that you detect things if they are they are above the threshold, right? But what happens if in this case, imagine that this vehicle here was below the threshold. What happens is that you're not going to detect anything, right? And this, your car might decide that in this case, well, it can continue straight and you might result in a collision. So inherently, although you have some evidence, detection doesn't need to explain everything, right? And potentially you can end up with, in situations where you basically are not aware of everything that is around you. So how can you actually remove this dependency on detection and on thresholding? So one thing that we can do is, well, instead of doing detection, right, predicting, where the objects are in the scene, instead we can treat this as a soft problem where our perception algorithm is basically going to do, it's going to predict semantic occupancy over the current time step, as well as the different time steps into the future that are required for the planning horizon. And if you do this, then basically there is no thresholding anymore, right? Instead, you have some occupancy probability of where potentially something could be. And you can do this in a way that is semantically aware. So you have different layers, if you wish, of this semantic occupancy forecasting for different types of actors. And what is nice about this representation is that typically with motion planners, what you do is that you rasterize detections and your prediction into the future in order to compute your collision costs and things like that. And here directly, you can use this these occupancy representations, which are probabilistic. The particular architecture we utilize is using a recurrent update such that you can predict consistent probabilities as you go across time. And in terms of the planner itself, so basically, it's going to be also very similar. We're going to sample a whole bunch of trajectories, and then we're going to cost the trajectories and select the one with minimum cost, where the cost is going to be a combination of learned cost and costs that use prior knowledge, for example, for safety. So these are things like, for example, you want to avoid, so this cost, for example, represent things like you're going to avoid regions that have high probability of occupancy. You want to drive comfortably, right? You want to follow the route because you're intended to go somewhere in the first place. And for example, you don't want to deviate too much from the center of the lanes, etc. And as I said, basically you sample trajectories, you evaluate all these costs, and you can select the one with the minimum cost. And you can train this also end-to-end, where you have some cross-entropy loss for the semantic occupancies. And again, we have this max margin loss for the cost, max margin loss, for the planner, right? Because we don't know what a good cost for motion planning is in the first place.
Sorry to interrupt.
Yeah.
We have 5 more minutes.
Okay, cool. So this works really well in practice, and in terms of you end up with less collisions and more accurate, I guess, other metrics for planning. And this is just showcasing. In this case, it's open loop, so the observations are not re-observed. Okay, and this is just showing what the different actors did and what was our prediction in this future horizon of what they will be doing in the different colors. All right, so in the last 5 minutes, which I think is, perfect timing, I'm going to talk about, a little bit about simulation. So one of the key important questions to handle in self-driving is, how can we evaluate self-driving vehicles? How can we evaluate that they're doing the right thing and they're safe? So there is 3 ways that we do this in industry. And typically, we exploit a combination of these 3 things. On one side, you have a structured testing, which basically is the idea that you have repeatable tests in the test track where you use this kind of mannequins in order to perform, what the actors will be doing. And this is nice because it has high fidelity, it's reactive, but you cannot do, it's not scalable, right? It's very expensive to do this. You can do log replay, which basically you can capture the real world and then basically look at when you when you make changes to your software stack, how will you deviate from what humans did, right? That's another way to test. Or you can use simulation. And in case of simulation, what happens typically is that high fidelity simulators do not really exist out there. And it has the nice property that you can test safety critical, right? Because it's a simulated world. It's reactive because the sensors are going to be potentially, modeling what you will see if you did that particular action. But as I said, the high fidelity is a problem. So let's look at what we can do to create high fidelity simulators at scale. So typically in industry, when we talk about simulation, what you observe is that they start the simulation with bounding boxes and trajectories, meaning that we're only going to we're only going to test the motion planner. So you generate a lot of scenarios, you test your motion planner, and then you see, okay, did it do the right thing? However, typically the bounding boxes here are typically like ground truth. So you're going to have an overly positive estimate of how well you do. And then you haven't tested the full system, right? Because perception and prediction have particular noise characteristics and uncertainties that this thing is not going to capture properly. So the alternative, right, is to do a full closed loop simulation where basically we will need to do a sensor simulation. We will need to learn to produce what the sensors will have seen in that particular scene. And that's actually very difficult. But if we were able to do so, then we will be able to test the full system. Okay, and I'm going to show you briefly how to simulate LiDAR and how to simulate cameras. The typical approach out there is to exploit virtual worlds created by artists, right? And then use physics in order to render how it looks like. The problem of this is that it's time-consuming, it's very expensive, you can have only small scale, limited diversity, and it's not realistic. So instead, our approach to simulation is very different, which is we have driven millions of miles in the real world. So we can use this in order to generate what we have observed, both the background, right, the scenes, as well as all the possible dynamic actors. And then, so in this case, it's the background, all the actors, and we have a lot of different diversity, right, because we have observed tens of thousands of these actors. Then we can create our simulations by selecting where to simulate, placing the traffic, creating realistic traffic, right? And then rendering how the sensors will have seen the scene in this particular case. And we use a combination of physics and machine learning, okay? And let me show you how well this works. So on the left-hand side, you see the simulation, our simulation system. And in green is the output of perception. On the right-hand side is the real LiDAR in a very similar scene. And you see that, it looks fairly similar. But what is more important is that for the perception system, there is almost no difference between. It turns out there is only a 1% difference in terms of our simulation with respect to the real world, where if you use something like Carla simulator, you see 25 points of difference absolute in IOU. So you cannot use this for testing, but this is very, very realistic, so you can really use it for testing. You can use this also to create safety critical situations that you haven't observed before, like coming out of occlusion, and then basically test your system. And then you can do this at scale in very different scenarios across all these domains that you have basically drive. And this is how you get the scale, right? With, all this is automatic, so it's actually really, really cheap. And you can do a similar thing for cameras, where the idea here is that we're going to insert vehicles that are fake. But in this case, they are 3D aware. So I'm going to let you guess which one of these vehicles is fake. So that one was fake. What about here? So, and we do this by inserting vehicles that were in different logs captured in a different place in the world. But everything, as I said, is 3D aware. So in this case, we can handle occlusions. That's another case. I think this one is a little bit more obvious. So this one is fake, right? And then we can simulate this also over video, right? And basically, so we reconstruct these assets, and then we animate them, and then we insert them in these videos, okay? And the good thing about this is that it's actually consistent across images as well as LiDAR. And in this case, we can simulate how multiple cameras mounted on the car will see the same scene in a consistent manner.
Sorry,
Cool.
we
So,
maybe have only 1 or 2 minutes.
No, it's gone. I'm finished. So today I show you a lot of autonomy, including things like perception and prediction, right? Neuromotion planner, and vehicle-to-vehicle communication. And I show a little bit about how to do simulation. There is a lot more things that we do in the lab, like mapping and localization. Also a lot of things on adversarial examples, how to get better neural networks, like unsupervised learning, compression, neural architecture research, etc. So, and there's still so much more that needs to be done for self-driving, but hopefully today you saw a little bit of what are our thoughts into what is the software stack of the future that we are building, and how the different progression steps into how you start with something simple, and then you basically add more and more levels of complexity as you observe what are the failure modes in the real world. Thank you.